Alright, I'm going to show you how to add vectors together graphically. I should have done that a while ago, but I didn't think it was that useful. But it's a somewhat useful skill. So let's say I have a vector like this, and I'm adding to it this vector. You can move one vector to the head of the other one. So the arrow is the head, the non-arrow side is the tail. So I can either move this one to over here, or I can move this one over here. And it makes a parallelogram. Where they meet is the new vector. So let's do, say I have a vector that is 0 degrees and has a length of 2. So I'll call this vector A. And I'll have another one that is 3, length 3, an angle of 90 degrees, vector B. And I'm going to add them together. So A is equal to 2, comma, angle 0 degrees. Its components. So there's two ways of writing vectors. You can do it the magnitude and angle, or you can do it as components. Component-wise is be 2 to the right, 0 up. And then B will be 3, comma, angle 90 degrees. Or writing it in component form, it would be 0 to the right, comma, 3 up. So to add these together, you have to convert it into the component form anyway. And then add the components together and then combine it. So the component form is 2 to the right, comma, 0 up, plus 0 to the right, comma, 2 up, 3 up. Adding them together, I get 2 to the right, comma, 3 up. And so my new vector, I'll call it C. And you either write it with a double arrow, or if you're lazy, you'll do it with a single one. Just because of the speed of writing it. But my new vector would have these components. To get it in angle form, the magnitude of it would be equal to the component squared, the sum of the components squared. So 2 squared plus 3 squared. So that's the square root of 13, which is equal to 3.6, roughly. And to get the angle, theta would be the inverse tangent. Measuring it off of the x-axis, the right x-axis, you need to know what quadrant it is. So this is 2 to the right, 3 up. So so the 3 up component is your vertical, or opposite of the angle. And your adjacent is 2, so opposite of the angle is 3 over 2. And it's equal to 56.31 degrees. So C is also equal to 3.6, comma, angle 56.31 degrees. And so if you draw that, let's draw you could also do the parallelogram method. This angle here is 56.31 degrees, and this length right here is 3.6, roughly. So, if you need to estimate what direction a vector would be, it's a good way of checking to your answer. Like if you do a rough sketch For example, let's say that you have a box and we have some forces on it. Let's say a rope is pulling it this way and another rope is pulling it this way. And you want to figure out what direction it will go. Well, copying the same length of hair, we see a parallelogram. You should be able to see that it's going to go in this direction right here. It should be down slightly to the left. When you do all your math, you should get angles and magnitude. This is a little bit shorter than both of these. So you should get an answer that's a slightly smaller in magnitude or comparable in magnitude to these with an angle that's pointing down and to the left. So electrostatic forces. Given two charges of magnitude Q1 and Q2, separated by a distance of d, the magnitude of the force that each of the charges exerts on the other is calculated by the relationship given by Coulomb's law. The direction of the force is determined by the fundamental law of charges. So what direction it is depends on whether or not they're like charges or opposite charges. The forces must be equal and opposite and equal and opposite. So even if you had a millionth of a coulomb versus a billion coulomb charge, they'll exert the same force on each other because of Newton's third law. And the K, or sometimes Ke, is Coulomb's constant. Electric fields are the energy field that surrounds any charged particle. Any other charge in this field will experience a force. So this electrical field, which is measured in newtons per coulomb, basically tells you that if you put any charge in this field, it will undergo a force. And for some reason, this PowerPoint is timed every 30 seconds. It wants to skip ahead. So electric fields and electric forces obviously are vectors, but electric fields are also vectors. They have a magnitude and direction. So you shouldn't think of a field as being like a fabric spreading. You should think of it also being as a direction. It has an arrow with it at every point in space. The direction of the electrical field is defined by the direction of a force on a positive test charge. So to figure out what direction it'll go, you imagine you put a tiny little positive charge in the field and see what direction it'll move to. That's just by definition or convention. Thus, electrical fields are always in a direction that is away from positive charges and toward negative charges. If a charge is placed at point X in the field, where the electrical field strength is E, it will experience a force that is proportional to that field strength. And the magnitude of the charge, so F equals QE. Now, if you know the force and you know the charge, you can calculate the electrical field that way too. I'm not going to go over electrical potential energy too much. But just like with gravitational potential energy, so you should remember that gravitational potential energy is equal to mgh. So what we have is G, and if you remember, force is equal to, what was the unit? Was it capital G? M1, M2 over D squared. And I'm going to just make this an H. It's supposed to be an, I'm just going to use the same value here. So this portion is lowercase g. So G is going to be equal to this gravitational constant times the mass of the planet divided by some distance squared. How do you go from this to this? So we took and basically, see if that's correct. Or let's actually plug this in, I should say. Let's plug this into this formula. So if I plug this into the formula, I get M times capital G, and I'll call this M1, and I'll call this M naught, divided by H squared times H. This H and this square cancel each other out, and thus I get that the potential energy due to gravity, another equation for it, is the constant times 2 masses divided by H. Is another way of reworking out this formula. And if we look at here, it's the exact same thing. Here, we just don't use MGH because in gravity we have a constant radius and we have a height, additional height. And here we're not going to have anything. It's going to always be the same distance. We usually aren't orbiting a charge. But it comes out to be the same equation. We have some constant times 2 charges divided by d. It just comes out to be that same same thing for potential energy that's electric, for gravity, working it out. Which, even though I've never seen this equation ever used, what that means is the potential energy for electric should be equal to some charge times the electrical times your distance. That should be QED. Should be the equivalent to for potential energy. I'm not going to really go over charge distributions either. Charge density, or charge per unit length, is represented by the Greek letter lambda. It's calculated as the total charge divided by the length. So you figure out how many charges are here, and a positive and negative charge are in the same spot. They basically cancel each other out. That's why you'd say the charge of an atom is 0, because it has the same number of protons as electrons, and the proton and electron has the same charge, except for opposites in sign. You can have charge, surface charge densities. If you want to go through the math, here's the calculus required. Basically, you think of it as being an infinite number of charges, and you just count to infinity. When you get done, there's your answer. That's quite literally what they're doing. They're summing an infinite number of infinitesimal small charges. They know that because it's symmetrical to the left and right, you can assume that the sum of forces to the left and right is 0. So you're only going to have a force in the left direction. They figure out these angles, add them all up, all infinite number of them. That's an integral. Integral adds up an infinite number of infinitesimal points. Do your law of calculus, and you get this formula. You can do that for any single thing, any single shape. Of course, the shapes get way more complicated, and you have to figure out how every single infinitesimal point will contribute, add up all the vectors. It's quite complicated. If you do this, take the physics class in college or university level, you will have to do this for any generic shape. Always hated line integrals. I could have swore I had a normal PowerPoint over this. You even see that K have a subscript of C for Coulomb. Coulomb's constant. And I really cut down electrical side significantly. We don't go over. Too much. I think I'm almost ready just to review tomorrow and have the test Thursday. It's not. I broke this up. It doesn't get interesting until after I introduce magnetism and then combine it with the electro to make electromagnetism. I think this was my throwaway test because it only introduces those two formulas. Let's go through this PowerPoint. So, an electrically charged object sets up a force field. This force field is known as the electrical field. To help visualize an electrical field, look at a group of grass seeds suspended in a fluid. If you were to put like some particles and floating on water, they'll actually get you can start visualizing charges, as some of the charges will go off and you'll start seeing them orient and interact with each other. So putting a small positive test charge in a positive charge environment, arrows point away, and negative charge, they point toward. If you put a negative charge next to a negative charge, it still points away. Usually, unless otherwise mentioned, you assume your test charge is positive. So the magnitude of the electrical field is equal to the force on the positive charge divided by the amount of charge. This definition assumes that the test charge is small enough that it does not disturb the position in any other charges in the system. Here you can see they're using the absolute value around the charge. So we don't use the charge's positive or negative sign. We are going to we're not going to be rigorous in our mathematics because it's too complicated. You have to keep track of a lot of vectors and stuff like that. That's beyond the level of high school. So don't plug in signs into the equation. Just keep track of whether or not it's repulsive or attractive. And then add your sign respectively. Here's some examples. The electrical field due to a point charge decreases rapidly as the distance from the charge increases. The field never actually goes to zero. That means that the electrical field from a single charge goes out to infinity. It will pull and push on something on the opposite side of the universe. But it's almost zero, but not ever equal to zero. And also, as you get closer and closer to it, it goes to infinite charge. Happy birthday, Nicole.
Thank you. Thank you. No, I had a morning.
She has a Coke in her hand. She obviously went to the store.
No, my mom got that for me. I had a possum try to attack my dog. And now she's just eating its tail. Bria. It was in her pen. Yeah, I had to deal with that.
By the way, these lines, when you do it, are called field lines. The lines are closer together near the charge and farther away to go out. When you're drawing field lines, you just choose an arbitrary amount. A density, basically. And when you draw them, you'll see that they get closer and closer together as you get closer to the charge, and they get farther and farther away. So it depends on how many lines you start out with. If you have two light charges, right in between them, there's zero force or zero field. Whereas if you have two opposite charges, what would be the strength of the field in between? It would be double of if it was just one charge. So, let me look and make sure. I could have swore I did it. This is an important concept of having two plates that are charged. And we use this quite a lot in physics. We'll charge up two plates. It's very easy to do. You hook one plate to the positive side of a terminal of a battery, and one plate to the other side of a battery, and over time, one side will become positively charged, the other side will be negatively charged, and you basically have two square plates that have a charge density over them. You basically make yourself a capacitor. Yep, so if two plates with opposite charges are placed parallel to each other and separated by a finite distance, the result is a parallel plate capacitor as shown here. The electrical field also is very unique. What is unique about this electrical field? The lines are just straight. They're all parallel. So if you wanted to create a parallel uniform field, you take yourself two plates, and as long as you're not near the edges, we have a basically parallel field inside. As long as you're not near the edges. So it's uniform, it's the same strength everywhere, except for close to the edges. And they're all parallel versus whenever you have something like this. Now they're all going in random directions. And it doesn't matter how... I want to say it doesn't matter where you're at in it. Whether or not you're right here or right here, it's all uniform strength while you're in between the plates. It's kind of like what we assume with gravity. Since gravitational field is so massive around Earth, we don't really, if we take a ladder to the roof, we don't feel much lighter. We don't start floating. And if we dig a little hole, we don't feel crushed by gravity. It's basically uniform right here. And since the Earth is so big, it's almost parallel everywhere. And if we don't walk a couple of feet, we don't start drifting and falling forward. I think it is uniform to... I didn't read. Electric potential energy. As you build up potential energy, occasionally you can get an electron to move. And once it starts moving, it'll create a bigger potential for the spot, for the hole it left behind. Thus another electron will jump over to fill that gap. Another electron, and you get the flow of electricity. Is this uniform, though? Yeah, so the field in this case is uniform between the plates and 0 outside the plates. This case is ideal, which is exactly true for infinite plates, and a good approximation for large plates. So, because these lines are the same distance apart, so normally, when you have something like this, if I were to look really close to it versus really far out, the same area, we can see it gets weaker the farther away you are. But if I look right here, and I'm really close to this plate, and now look in the middle, and I look very far, you'll notice that the fields never get less dense. This means that any single point inside this field is the same strength. It doesn't matter if you're right next to the plate, in the very middle of the plates, or on the other side of the plates, you get the same strength. It's completely uniform while inside of a field, and it's parallel. Whereas here, there's obviously different densities. We can assume on the surface of the Earth, gravitational field is basically parallel and uniform. At least on the scale of humans. We're not going to go into capacitance. So, what does this mean? Let's say that we have a parallel plate like this, where all this side is positive, and this side is negative. And let's say, like a baseball, we throw a charge in here with this positive charge. What is it going to do?
It's gonna repel from positive to negative.
What shape is the curve going to look like? So let's do another example. We have Earth. We have gravitational field pulling downward, just like we have an electrical field pulling downward here. I throw a baseball. What's the baseball going to do? It's going to fall like a parabola. As soon as this enters this place, it's going to behave just as if it was a baseball under a gravitational field, so mass under a gravitational field, or we have a charge in an electrical field. The equations are very, very similar. But I think that's it for today.